So this is 5.3, number 1, and we're given this graph, and you're asked to come up with a number of values. I don't think that part A was the part that people were having trouble with. Part B is asking on what interval is G increasing? And in this case, G is, so my function G of x is from 0 to x of f of t dt. So this is the picture of f of t down here. So we're thinking our G function is our cumulative area function, and we're asking, G gets bigger and bigger and bigger as I accumulate positive areas, and then G is going to get smaller and smaller as I start accumulating negative areas. So when it asks on what interval it's increasing, that's the same thing as asking when is f positive. Because those two things, if f is positive, it means that I'm accumulating positive area. So I think, given this scale, the interval should be from 0 to 6. F is positive, and so G is increasing. And I think that there was another student who inputted this and got the answer marked as wrong, right?
I had 0 to 3, my scale is different.
Oh, okay. Yeah, so for this, the way that mine is displayed, they're every 2, but if your scale was from...
Mine's, goes to 5 is where your 10
okay.
is, so.
Oh, okay.
Yeah.
So it's like half as much, they just
Yeah.
changed the scaling. And if I think that this might be an error in the programming. So in general, the places where it switches from increasing to decreasing are going to be where my derivative function is equal to 0. You can think of this f function as your derivative function, and so when my derivative is 0, that's when my function has a critical point, and that's in this case here at this point. So hopefully you're thinking about it right, even if maybe
yeah,
it's...
I had 0 to 3, and it exactly would have been
It
0
looked
to
exactly
6,
like
so,
that.
Yeah.
Okay, so I'll send them an email. Tell them that they're wrong. The next one I want to talk about is number 6. Let's see. Oh yeah, this is one that I guess, was it number 6? No, I think it was the one that had the functional bounds. So it was number 7, sorry. Yeah, this one's the one that's much harder. Well, you guys are experts, so it's probably, not that hard, but I think it's sort of a hard one. So we're looking, y is the integral, and the bottom of this is a function, and mine is written as 2 minus 3x to 1 of u cubed divided by 1 plus u squared du. So the important thing with this is that we're going to apply fundamental theorem of calculus. We want to find dy dx. So we want to take the derivative of this crazy function with respect to x. So the first thing that's wrong is the fact that our variable is at the bottom of this function. So we need to, in order to apply fundamental theorem of calculus, we have to rewrite this by interchanging the bounds. And when we interchange the bounds, that's the same thing as taking the negative of the function. So I'm going to say that this is the negative of 1 to 2 minus 3x u cubed over 1 plus u squared du. And one of the things that I want to point out that's an important theoretical concept is, well, it depends upon what x is, right? Because for certain values of x, it's going to be to the right of 1, but for other values of x, it's going to be to the left of 1. And my comment is, the integral notation takes care of that it really doesn't matter whether the value, it does mean that it might not correspond to the area anymore, because if I'm traveling backwards, that's going to give me a negative value rather than a positive value, but I don't have to worry about that here. So we have this new function, and this looks much more like what we want to use to apply fundamental theorem of calculus. So let's take the derivative of both sides, and when we do this, we're going to have to use chain rule. And this is something that I think I should have written more explicitly in the video that we recall chain rules when I have a composition of functions. Let's say I have g of f of t, and I want to take the derivative of this with respect to t. That's the same thing as taking the derivative of the outside function evaluated at my f of t function times the derivative of the inside function. And we're going to apply exactly that idea when we take the derivative of this. So in this case, when I think about taking the derivative, so I'm going to look at dy dx, that's going to be the derivative of the outside function evaluated at our f of t function. In this case, this piece right here is my f of t function. So when I take the derivative we know by fundamental theorem of calculus is just the inside part. So I'm going to end up with 2 minus 3x cubed 1 plus 2 minus 3x squared. Maybe my words were awkward, but I think it's easy that we're undoing the integral by taking the derivative, and we're evaluating it. Normally we would just have x's here, but we have this whole function. But we aren't quite done yet. We have to multiply by the derivative of our inside function, which in this case the derivative is the derivative of 2 minus 3x, which is just negative 3. And I almost forgot the fact that when we flip the bounds, we got this negative sign. So we have the negative of negative 3 times this whole thing, which will just simplify to 3 times 2 minus 3x cubed, all divided by 1 plus 2 minus 3x, all squared. And that's our answer. And then finally, 5.3, number 10. It's the last one I wanted to talk about, unless we have other things that we want to talk about. Number 10? That seems like sort of a boring one. No? Yeah. Let's take a look. Let's take a look at 5.3, number 10. So here we're asked to evaluate the way that mine is written. I'm looking at the integral from pi over 6 to pi of sine of theta d theta. So what I always do, maybe this is helpful for you or not, I think of taking the derivative of sine gives me cosine. Like this is my forward direction taking a derivative. And then, so that means that when I go backwards, my antiderivative is going to give me negative cosine. I don't know. That's not a very helpful graphical device for you, but really there's nothing logical about it. It's something that I end up memorizing. So that just tells me that when I take this antiderivative, the antiderivative of sine is negative cosine of theta, evaluated from theta equals pi over 6 to pi. And so I'm going to plug in these values. I'm going to have to be I'll write it down here to be really careful. So this is the upper bound minus the lower bound. So I'm plugging in negative cosine of pi minus the lower bound, so minus negative cosine of pi over 6. And this is where I might have to go back to the unit circle to recall what these values are. I'm going to try to be exact in the values, and maybe this is the problem, that entering decimal approximations gave answers that didn't work out. I know that the cosine of pi is going to be down here at negative 1. So this is, the cosine of pi is negative 1, so I get the negative of negative 1 minus the cosine of pi over 6. If I break up pi into sixths, I see that the cosine of this should be, cosine of pi over 6 is 1 over the square root of 2. Right? Yes, I think so. So that when I evaluate this, no, 1 over square root of 3. So this is something that maybe this is the problem, that I should look at my unit circle and I should have this memorized, shouldn't I? And if I did have it memorized, then it would give me the right answer. Let's look. Cosine of I have pi on this calculator somewhere, right? E? Somewhere? There we go, pi. Divided by 2. And if I had, oh, no, I didn't want pi over 6, yeah. I knew that, I have that one memorized. Yeah, and let's say 1 divided by 2 to the 1/2. Oh, that's wrong. Oh, 1 divided by 3 to the 1/2. Oh, it's square root 3 over 2. Thanks.
That's when I did it on mine.
Because you have a smart calculator, probably. So this should be 1 minus negative square root 3 over 2. Let's see if that's... Yeah, that's what this gives me. Thanks. Or a decimal approximation of about equal to 1.866.